Hello everyone, welcome to our discussion of section 7.2 where we will be talking about using integrals to calculate volume. Now before we get started, I'd like to give this, as you can see on the screen, the creator of this website credit, Patrick JMT, and where I was able to find several nicely done examples. So some of the examples you see in today's lesson I adopted from his work here, and I wanted to give him credit. Also, his website contains many other good videos on other topics in mathematics. So you're welcome to visit this whenever you have time. Now let me switch over to the dock camera so we can continue with our lesson. All right, so here's the applications of integration to calculating the volume of a solid of revolution, or just a solid that we are given. So that number 2, where it says solid, that means if we are given a solid, then how do we approach finding the volume of the solid using some integrals. Now, you're already familiar with application of integrals to finding the area under a curve. That's whenever we evaluated a definite integral so far, that's what we were doing. We were calculating the area under a curve. But what this section does, it takes this method a step further, and it uses the area under the curve to calculate the volume of a solid that is going to be generated when we rotate that area under a curve about a certain axis. It could be either x-axis, in which case we will say dx, or we integrate the expression along the x-axis, or it could be dy, in which case it means we are integrating along the y-axis. The other key thing here to remember is that when we refer to solid of revolution, we're just referring to the object part of a volume. So for example, if you take a look at a common household cup, that household cup has a volume that takes in water. But we're not talking about calculating that volume. That's the void, that's the amount of the volume that is dedicated to containing some liquid in the cup. That's not what this methodology does. What this does is it calculates the object part or the solid part of that cup. Or if you have a cone of some kind and it's a filled-in cone, then it calculates the volume of the solid portion of an object. So just keep that in mind. So volume of a solid of revolution, we have two methodologies that we can use to accomplish that. One is called the disk method, which you can see on the screen here. And the other one is called the washer method. Now, why do we have these two different methodologies? The reason is that the area under a curve, as we use that area under this curve to integrate, let's say, between A to B along the x-axis, we can either model that area using a disk, that is a solid disk with no holes in it like a donut, and we call that a disk method. If we can use a disk to calculate that area, that volume, we call it a disk method. Or if the area portion under the curve that we can use to calculate the volume, if it's in the shape of a donut, or if it has a void in the middle, if it has that form, then we call it the washer method. So that's why we have these two methods. And of course, when we are given a solid, that is, if the solid that we have is not the result of a rotation of an area about a certain axis, but it's the solid that we've been given already, then for that we will use either the disk method, the washer method, or we will use the elementary geometry to come up with a cross-sectional area that would be neither a disk or a washer, but it would be appropriate for that particular solid for which we're calculating the volume. So we will use elementary geometry to accomplish that. Okay. So but categorizing the methodology helps us remember which method to apply when, right? So if we are able to come up with a cross-sectional area, because basically what we're doing is we're taking the integral of an area, but that area, it's a cross-sectional area of the area under the curve. So if that cross-sectional area is a disk, then this is the formula we can use to find the volume of the solid that is going to be generated by rotating that area around a certain axis. So this would be the formula. Integration limits, pi, of course we can put this pi in front because it's just a constant, times this f of x, in this case it would be that f of x, whatever that function, squared, and of course if we're integrating along the x-axis, we have dx. If we were doing the same thing using the disk method and integrating along the y-axis, the only thing would change is this would be dy instead of dx, and this function would be a function of variable y, because obviously we're integrating along the y-axis. So that's the formula we will use if we had the disk method. It would be a definite integral along the x-axis, in this case, pi times the function squared dx. And this is just a note saying that use dy if rotation is along the y-axis. Now, the volume of a solid revolution can also be completed using the washer method, which means the area that we're rotating about a certain axis, in this case it's the area between these two curves, for example, right? So these we will have examples just like this, but the function that generates this curve and then the function that generates this curve, each of these form the outer or the inner radius of the washer that we end up with when we rotate that region, the region that I've shaded, about the x-axis, for example, as it's shown in this case. So we determine the outer radius, which is the distance from the farthest boundary. We're talking about these two curves forming the boundary, the farthest boundary to the axis of rotation. So for example, if we take this picture, if we were rotating along about the x-axis, then the outer boundary would be this one with respect to the axis of rotation, or R1, which I've labeled it here. And the inner radius of rotation would be this line, this straight line, with respect to this axis. Okay? Why is that important? Because then, as you see in this formula, then we can integrate from A to B, or from A to B, from this point to that point, and then of course the times pi times outer radius, which would be R1 in this case, squared, minus the inner radius, which would be R2 squared, and dx. And again, once again, we use dy if rotation is along the y-axis. And that's that. So then we can continue the lesson with how to set up integrals using the disk or the washer method. So this is pretty important. Why? Because as you'll see, in all these examples, whether we're using the disk method, the washer method, or using elementary geometry to come up with a cross-sectional area to integrate, to compute the volume, the integrand, the terms in the integrand are very, very simple to integrate. So it's not going to be a big deal at all to integrate the expressions. But what's going to be a little bit challenging is sometimes when we have a solid, to come up with the cross-sectional area for that solid, which we then can integrate to calculate the volume. So finding that integrand is key in this section. Taking the integral, calculating it, it's not going to be a big deal at all, as you'll see, because so far we've calculated some complicated integrals. But in this section, the integrand will be simple, but coming up with that expression to integrate, it's going to be, sometimes it's going to take a little bit of working around elementary geometry, which most of us have dealt with a long time ago. When I say elementary geometry, I'm talking about, the sides of a square are equal, the sum of the angles in a triangle add up to 180 degrees, and what properties right triangles have, what properties isosceles triangles have, what properties similar triangles have. All of this goes back to elementary geometry. We will use that if needed. If not needed, if we have just a disk or washer method, it's easy. We will use these formulas. We will use one of these depending on whether we have a disk method, we have a disk or a washer, we will use those formulas that I boxed. That's pretty straightforward. But when we do not have those cross sections, either in the shape of a disk or a washer, then we'll have to use elementary geometry. Okay, so the bulk of this lesson today, not exclusively, but the bulk of the lesson is to find just the integrand, just to find that expression that we can then integrate. That's the bulk of the lesson today. Because once you take it that far, the rest is really, really simple expression to integrate. You're going to have expressions like x minus x squared plus x cubed, something like that. So those are easy expressions to integrate. So in this case, in this example, we want to set up the integral to find the volume of a solid by rotating this function about the x-axis. Okay, so let's draw a quick picture of this scenario. And that's an easy function. We've seen that square root function back both in Math 126 and Math 127, which are the pre-calculus 1 and 2 courses. So that shouldn't be a problem for us to draw that. Okay, so we have the x-axis and the y-axis, and that function would look something like this. Something like that, an increasing function like that, right, for all x values from 0 and larger. Okay, so we want to find the integral, or set up the integral to find the volume that results from rotating this function, and let me label it actually, and I want to label this as y equals square root of x about the x-axis. In other words, if we do that like that, and I'm just sketching what would this solid look like if we do what this problem is saying, then we would have basically, what do you think? Would we have a washer or would we have a disk? So we would have something like that. We would go like this. It would be solid, right? And it would have a thickness, right? It would be dx, right? That's delta x, let me call it, which would be dx in terms of an integral. And if I use my pencil to shape this. So what do you think this is? Is this a washer or a disk? It's certainly a disk, right? It's a solid disk when we rotate this function about the x-axis, not a washer. So our formula would be this. Would be take the limits of integral. We need to find that. And then pi times f of x, the function, which we have square root of x, squared dx. That's going to give us using the disk method. Okay, so if we do that, we will get, so this would be a solution. The picture itself is also a part of the solution, because in many problems like this, you will have to draw the picture. So a little bit of having an artist in you, it would help in this section. But if not, it's still no big deal. Even a very basic elementary sketch would help us visualize whether we have a disk case, whether we can apply the disk method or the washer method, or we should use the elementary geometry. So using this is using the disk method. That's obvious from this picture. Using the disk method, we have the formula for the volume, that is V equals limits of integration from a to b pi times the function, the function of the curve, and that function squared, and we're rotating along the x-axis, so we have dx, right? So if we substitute, so let's call this, we can take this vertical line that I've drawn, any x value, but let's just say that's x equals 2, right? So we want to integrate using the disk method. We want to integrate from this point, which is 0, to this point. If you want, you can pick this to be x equals 10, if you wish. But that would then stop the integration from 0 to 10. In this case, I'm taking the integral from 0 to 2. So a would be 0 and b would be 2 in our case. Okay, so then the volume would be 0 to 2, right? Let's not forget this pi. This pi should not be forgotten. So let me just highlight underneath it. It's a pretty important part of the formula. And I'm going to put it in front here because it's just a constant. And then this function, of course, is because we're rotating along the x-axis, so it's going to be the variable that we're integrating is x. So I'm just going to keep it as that. So we will have square root of x squared dx. Okay, so what would the volume be? The volume would be pi integral from 0 to 2 of square root of x squared is x, right? dx. So this is, again, let me remind you, we're just practicing how to set up the integral to find the volume, right? Because once you have this expression, then I'm sure you can integrate to find the volume. So integrate to find the volume. Okay, so that's just 1/2 x squared, right? When you integrate, and then you calculate the definite integral as we've been doing so far. So we're just going to make sure that we know how to set up the integral for each case. So in this example, we're asked to set up the integral to find the volume of a solid by rotating this function, the cubic function, about the y-axis between y equals 8 and y equals 0. So this is a little bit different, right? So let's try, with all these examples, by the way, I know many of us, including myself, prefer not to draw too many things, but it helps if you do. So, and I know it helps me visualize the problem better. So let me try my best, even though I'm not so good at this, to draw a half decent picture to help us see what this problem is asking. So we have the volume of a solid, and so this is by rotating this function about from y equals 8 to y equals 0. That's pretty critical because the cubic function, as we learned in pre-calculus, it's going to go something like this, right? And then it's going to, I'm going to draw the rest of this dashed. Let me draw the rest of it dashed because that's the portion, that portion we don't really need, because we only are asked to integrate this function between the two lines, these two horizontal lines, y equals 8 and y equals 0. So y equals 0 is basically this, right? Just the x-axis. Now y equals 8, if I draw just a basic, that lightly at least, maybe I should use my pencil for that. I didn't this time, but that's y equals 8, and here the x-axis is our y equals 0, this one. So we want this this function, and I should label it that. This is y equals x cubed about the y-axis this time. So we've learned in the previous section, or the one before that, that when we take the integral about the y-axis, then our integral is dy, and then this function has to be written as x in terms of y. So we're going to need to rewrite this expression as x in terms of y. So we're going to need to do that. But if we do that, if we rotate, and I'll use my pencil for that, if we rotate from y equals 0 to y equals 8, so that would be along the y-axis, about the y-axis. So what are we going to get? Are we getting, what do you think this is? If we rotate that function about the y-axis, what are we going to get? We're going to get a washer or a disk. What do you think? That's going to be a disk, right? This is again a disk, a solid disk, right? There is no hole in the middle. This is not a washer. This is a solid disk. So when we set up our solution, then we say use, the first thing we establish is use the disk method, right? We have a solid disk as we sketch this drawing. So, which is volume calculated as pi from, it's a definite integral from a to b, pi times f of x, f of y, I should say, f of y squared dy. dy because we're taking the integration along the y-axis. Maybe I should dy because we are integrating, this is pretty important, along the y-axis. Okay, so that means this function that we have is now f of x. So we need to rewrite that as f of y. So let me start that here. So if y equals x cubed, then raising both sides to 1/3 power, right? Raising that, we are able to say to have let me switch things around. So that would be x equals and y to 1/3 power, right? So now we have x in terms of y. This is helpful when we integrate along the y-axis. So our functions here, f of y, would be y to 1/3 power. Okay? All right. So now, and the limits of integration, what do you think? What would be a and b then? If we're integrating between these two horizontal lines, then the limits of integration would be from 0 to 8, right? So let's put that all together. We have everything we need. So we have the volume equals integral from 0 to 8 pi times this function, y to 1/3 power dy. Okay. And of course, let me not forget the squared part, right? That's the formula, right? Like that. So this is, so the pi, very important, and also we have squared there. Okay, so the power and the pi, they're all there. And then we can multiply. So what do we get? We get the volume equals, and I can put pi outside because it's a constant, integral from 0 to 8 of y to 2/3 power dy. Okay, so this is the setup for the integral we need to calculate to obtain the volume of the solid volume of such an object that is generated by this portion of the cubic function about the y-axis between y equals 0 and y equals 8. Okay, and I'll just say, because I know this is pretty easy to integrate, just add 1 to the power, divide by the new power, that's all. So integrate to find the volume. But from this point forward, it's pretty easy. And if you have any questions, of course, you can always come to me. So that's that. Okay, so in this case, we want to set up the integral to find the volume again of a solid by rotating a region enclosed by these two curves, y equals x and y equals x squared about the x-axis. So we're integrating about the x-axis, so that's again dx. So we don't need to change these. We can take these functions as they are. Okay, but let's again draw a picture to help us visualize what is it that exactly we're doing here. So I'm just going to draw the picture here. Maybe here a little bit like that. Okay, and then so x squared, y equals x squared, it's pretty straightforward to function to draw. It's just a basic quadratic function. Let me try my best to draw this as best as I can, but if it's not to scale, please forgive me for that, but I'll try doing that. Like that. And that's the vertex of this quadratic graph should be origin. So sorry about that. So that's just, it should be perfectly at origin. Mine is a little bit off. So this is our y equals x squared. And then also y equals x is the straight line that dissects this first quadrant. So let me try to get that. I'm sure I'm going to be off, but I'm going to be off a little bit intentionally because I want my graph to look a little bit legible as you see this on the screen. So let's just assume this red straight line is y equals x. I'm sure I'm off. So this should be perfectly dissecting the first quadrant, by the way. But I just drew it like this because I wanted you guys to see that the region that we are rotating this time is this one. It's this region. Okay? That region is what we're rotating, and we're rotating about the x-axis, so we need to know what that point is, because the limits of the integration are going to go from 0 to that x value, whatever that is, whatever they intersect. Okay, so we need to find what that point is. Let's find that out. So that point here, let's call it for a question mark. Well, we know that that point is the intersection of these two curves. So we can set it up like that, y equals x squared. And then from that, we can say x equals x squared. And then we can say x squared minus x equals 0. Factoring the x out, we get x minus 1 equals 0. And then, of course, from here, we can say x equals 0 and x equals y. 1, okay? And if x equals 1, then we know y should also be 1, right? So that point, the coordinates of that point are 1, 1. And so this one is just the origin. This is that. These two curves intersect at 2 points, 0, 0, which is the origin, and also 1, 1. Okay, so that's that. And so actually, from here, y equals 0, and from that 0, 0, and from here y equals 1, and then therefore we have 1, 1 as the other point of intersection, which both of them are now shown on the drawing. So let me also add a 0 there. Okay, so we found the region that we're rotating about the x-axis. So as you do that, what do you think we're going to get? Do you think we're going to get a disk or a washer? And let me draw just a dashed. As much as I know I can draw half decent drawings, I will draw these, but beyond that, I'll stop if I get to some complicated drawings. So if you take this region that is lightly shaded and rotate it about the x-axis, for sure we're going to get actually I didn't draw that very well. Let me erase that like that. So this red line, it will give us that, and the blue one will give us that. So for sure we're going to get a washer, right? It's going to have a hole in the middle. So we're going to have to use the washer method. Now the question is, if I bring back that first slide, using the washer method, we're going to have to know what length is the outer radius and what length is the inner radius. And we're going to square those and then subtract them and times pi and the limits of integration. So we need to identify the outer and the inner radius. And those are easy to identify because we're rotating about the x-axis. So the distance from that red line, which is y equals x curve, to the x-axis, notice that as we do that, that washer, the outer radius is on that line, on this curve, y equals x. So the outer radius, the distance from that red line to this x-axis is just x, because it's equal to y, right? So we can just call it x. Whatever y is equal to x. So we can then say, let me write that here, that I might as well draw some, it's a little bit crowded, this drawing. So let me just say that's, let me call that R1. I'll just try to write it in red. It's too crowded. R1, and this is R2. So this is R2, that one is R1. R1, let's take it as the outer radius, right? It's clear from the drawing. So we write R1 is outer radius. Move this up a little bit. So that's the outer radius. And what is it equal to? It is equal to x, because that's what the equation of that line is. Y equals x is that. Okay, so inner radius, we called it R2. What is that equal to? Well, that is equal to the distance from the axis of rotation, which is the x-axis, to that curve, which is x squared. So that is just x squared. Okay, so now we will apply that formula that we have. So volume using the washer method. So using, let me actually write here that using the washer method. Okay, and then we have, now the question is, where are we, from where to where we are integrating? We're integrating from 0 to 1, right? We found out that the x value component for that point of intersection is 1, and that's the region we're integrating. So from 0 to 1, pi, and then the outer radius would be x squared minus the inner radius squared. So inner radius is x squared squared, close bracket, and then we're integrating along the x-axis, so dx. Okay, you'll see that you're seeing that this is also a pretty easy integral to calculate. All right, so then we have, let's simplify this a little bit. So we have the volume equals integral from 0 to 1 pi, and that'll be x squared minus x to the 4th power, so, and then dx. So there's our integral. Okay, we can easily integrate that times pi between these limits. So I'm just going to add integrate to calculate the volume. I'm sure you're seeing that the most important part of this methodology to use integration to calculate volume is finding this integrand. Once we have that, the rest is really, really easy. Okay. All right, so let us go over another example. Here we are asked to set up the integral to find the volume of a solid by rotating a region enclosed by curves this and that. This is the same two curves as the previous example, but this time we're not rotating this region about the x-axis, we're rotating it about this line, y equals -5. Just like before, even if you don't like drawing, it's okay. Just draw a picture that helps you better visualize this, that's all. So something simple would do just as well as you see me do that right now. So and hopefully I can do a better job of drawing those two curves this time. And so I'll try. So maybe I should do this like that, like that, like that. So that's the vertex. This vertex looks a lot better than the previous time. And then so this is our y equals x squared curve, and let me draw a straight line that is more representative of y equals x, right, which should dissect equally that first quadrant. Well, maybe a little bit better, I don't know, than the previous one, but I want to draw these so that you can, this region that we're rotating is visible, is clearly visible. I don't want it to be too small that people have to squint to see what that looks like. But that's the region we're rotating, and we're rotating it about this line, y equals -5. So let me, again, I apologize that my drawing is not to scale for sure, because we know that that point from the previous example is 1, 1, and this is 0, 0. So if that's 1 from here to here is 1, then -5 would be way down here, but I don't want to draw it way down here. I just want to draw it roughly here. So my drawing is not to scale, but it should do to address the point that I'm trying to make. So let me draw that with my blue ink. I will draw this line. So rest assured, y equals -5, if this was drawn to scale, should have been further down. But I think for our purpose, this will do. This is y equals -5. And so that line here, let me just draw it a better, nicer dashed line. This is 1, right? That's 0, so 0 to 1. Okay, so now I'm sure you see clearly that if you rotate this region about y equals -5, you're not going to get a solid disk, right? Because we have these two curves forming the outer and inner radius of that region. So it's going to be a large bowl, basically. Okay, so it's going to be a washer, just looking at the picture. So the region of rotation, so we're going to use the washer method. So let me write that down from the get-go. Just looking at the picture tells us that. So using the washer method, right? So that's going to be our formula. So now we're going to have to figure out the inner and outer radius, first of all. But notice that because the line about which we're rotating this region is parallel to the x-axis, so it would be similar to that, it would be dx, right? So we don't have to change these functions and write them as x in terms of y. We can use them as they are, y written in terms of x. So that would make our work a little bit lighter, but we still have to figure out the inner and outer radius. Let me draw, maybe with my pencil, the inner and outer radius. So let me draw a light line to that line, right? You can barely see it on the screen. But let's call this, we can label these things anything. So let's call this I guess R2, R1 if we want. So this would be, what do you think? Would this be inner or outer radius if you're rotating about this line? It would be the inner radius, right? So R1 is the inner radius. Oh, I didn't mean to write that with my pencil, so I'm just going to use my red ink. So R1 is the inner radius. And then let me, with my pencil, if I can find it here, draw the outer radius. So outer radius, as we rotate about this line, it's going to be the y equals x line again, right? So it's going to be this one. So that would be the outer radius again. I'm going to draw an arrow from that line to the axis of this axis about which we're rotating. So this is R1 and this is, let's call this R2. All right? So R2, or the outer radius. Okay, so now, and we are integrating from 0 to 1 again. That's not going to change at all. All right, so we have everything we need. Let's put them all together. We have the volume equals integral from 0 to 1, right? From 0 to 1 about this line. So, and then pi times the outer radius squared. And the outer radius here, let me actually write them first. Before I transition to here, I wanted to write it here. So R1, or the inner radius here, right? The distance from that curve to this, never mind the negative. Look at the distance. The distance from this line about which we're rotating the whole region to the x-axis is 5, right? 5 units, never mind the negative. 5, and then plus whatever that x squared is. That curve is x squared, right? Y equals x squared. So 5, the inner radius is 5 plus x squared, which is the distance from that line to this. So we have 5, so right here, so 5 plus x squared. That's our inner radius. Now the outer radius, which is that, is the distance from this axis about which we're rotating all the way to that y equals x line. So from here to the x-axis is 5 units, we know that. And then 5 plus x, whatever that point is on the y equals x line. So that would be 5 plus x. So you might see these two, and you might say, well, wait a minute. How come 5 plus x squared is inner radius? How is that even possible? This is a larger quantity than that. This should be the outer, this should be the inner. You would be right in your observation if this quantity was taken outside of 0 to 1 region. But between 0 to 1 along the x-axis, and you can use this on your calculator to see, between 0 to 1, 5 plus x is actually a larger quantity than 5 plus x squared. I mean, you can pick any number between 0 to 1 and try it here, and you'll see. For between 0 to 1, 5 plus x is a larger quantity than 5 plus x squared. Let me actually write that. So for, I'll just write it underneath here. So for x between 0 to 1, R1 or R2 is either greater than or equal to R1. Okay, but for x values between 0 and 1, R2 is either greater than or equal to R1. Just remember that. So that's why this is the outer radius, and the smaller value would be the inner radius. Okay, so the formula, according to the formula, we have outer radius squared. Outer radius is R2 in this case. Outer radius is R2, which is 5 plus x squared minus the inner radius, 5 plus x squared, and then dx, right? dx. We're integrating about a line that is parallel to the x-axis, and that's the equation of that. Okay, so that's that, and let's simplify this expression before we abandon it. So we have volume going from integral from 0 to 1 pi, and we want to expand these, right? So we have 25 plus 10x plus x squared minus 25 again plus 10x squared plus x to the fourth, close that, and then dx. And then, of course, after you distribute this minus into this parentheses and simplify and combine the like terms, you should end up with this integrand. So we have pi from 0 to 1 times, I'll just write the final simplified form, minus x to the fourth, right? X to the fourth power, after you distribute this, minus 9x squared plus 10x dx. Okay, so again, things that I've seen people leave out inadvertently are this pi and these powers. So just don't forget to raise these, the outer radius squared minus the inner radius squared, and after that we have the pi here, and this is this final simplified form. So you can see how easy each of these terms are to integrate. So after that, we can integrate to find the volume. Okay. So this time, as opposed to the previous example where we took the region enclosed between these two curves about the line y equals -5, now we want to take the rotation of that region about the line y equals 7. So as before, let's do our best to draw a picture of this situation, and I strongly encourage you guys to pause the video and try to do this on your own before you see my solution, and see if your solution matches this one. So here's my version of this graph. Okay, so we have the x-axis, the y-axis, and we've got, let's see, so we have I'd like to draw that one first, the quadratic graph, and something like that. It should be more symmetric than I'm drawing it, of course, but here's the best I could do, like that, with the vertex of this quadratic function being at 0, 0. And then let's draw that line as before. So we have that line that will dissect it is supposed to dissect equally that quadrant 1. So I will draw something that would show also the region we're looking to. So that small region, and I will shade it supposed to rotate about the line y equals 7. So let's also label, so this is y equals x, and this of course is y equals x squared, and that point we already know it's 1 comma 1. Okay, so then let's draw. This isn't going to be to scale because I go off the page if I drew this picture to scale, but let's say that y equals 7 is that horizontal line going across like that. So let's take that as our y equals 7. It would be higher if I drew this to scale because it's 1 unit from here to here, so 7 would be much farther up. But this will do. So we're taking the rotation of this region about that axis, y equals 7, and we want to determine the volume of the solid. So by now, for sure, the question of whether this is a washer or a disc should be completely settled in your mind, and this is certainly a washer, right? Because we have an inner boundary and an outside boundary, outside radius as we rotate about y equals 7. So why don't I just do a rough sketch of the inner and outer boundary. By the way, it doesn't make any difference whether you label this R1 or R2, or which one you label as R1 and R2, as long as you know exactly which curve represents the inner radius and which curve represents the outer radius. So we have let me label these as R1, and I'll just R2. And since we're going about rotating about that axis, so with respect to that axis of rotation, this curve, or y equals x squared, is the outside radius, and this one, or y equals x, is the inner radius. So let's write it down. So, and I will list how we should think about problems like this. The first thing we want to establish is whether we want to use the disc or washer method. So we establish we're going to use the washer method. Okay, use the washer method. Then for that we will need the outside and inside radius. So R1 would be the inner radius, and it would be equal to that distance, and then plus that curve that we have 7. So 7 would be the distance from the horizontal line to the x-axis. So for the inner radius, for the outside inner radius, it would be 7 minus that distance, which is on the line. So that would be x, right? So the inner radius would be 7 minus x. And x represents, because x and y are equal to each other, we're integrating about a line that is parallel to the x-axis. So we want to write all these, the inner and the outer radius, in terms of the variable x. And we know x equals y on that line, so it makes no difference if you say x or y. Of course, we want to use x because we're integrating with respect to this horizontal line. So I kept x rather than y. And then the outside radius, or R2, as I've labeled it in this picture, would be, again, 7 would be the total distance from that horizontal line to the x-axis. And then, of course, minus that distance that falls on the curve, right? That distance that falls on the curve is x squared, so minus x squared. Okay, and then the question of from where to where we're integrating it's going to be from 0 to 1, right? It's that that's that portion of this graph that we are integrating about y equals 7 line. So let's set up the integral for this. We have the volume represented as the integral from 0 to 1, right, from 0 to 1, and pi times the outer radius squared, 7 minus x squared, minus the inner radius squared, 7 minus x squared, dx. Okay, so both of these expressions are pretty easy to expand and simplify. These are just binomials squared. And we just want to know how to set these up at this point. And after that, we can just say then simplify this, simplify the integrand, simplify, then integrate to calculate the volume. Okay. All right, so that's another example. Let's do another one. Actually, I have that right here written up already, so that saves us a little bit of time. So this time the same two curves. We have that same region, but we want to find the volume of that region about the line x equals -3. So of course this line, it's going to be a vertical line parallel to the y-axis, so our integration is going to be with respect to the variable y. So for this equation, we're okay. We can just use y rather than x because y and x are equal. But here, it would make a difference because we will have to solve for x in terms of y. Okay, so that's why about which line we're taking the rotation, it's pretty significant thing to notice. And by the way, since we did it about y equals 7, I just want to put that symbol to indicate rotation about, the rotation is taking place about that line. Okay, so once again, let's draw the picture for this situation. So we have x-axis and then the y-axis. And then I want to do a quadratic graph again, like that. And so this is our y equals x squared graph. And then let's draw the y equals x line. And we have that familiar region, which we've used in several examples. And that point is, of course, 1, 1. And we have 0, 0 here. And this is, of course, y equals x line. Okay, so the axis of rotation, let's draw that as x equals -3. I will draw it somewhere here. Like that. So move this up a little bit. Like that. So this is x equals 3, and this is, we want to show that as the axis of rotation, so this region about that. Okay, so then of course this is going to be another washer as we take the rotate this region about that axis. And let me establish the inner and the outer radii. So with respect to this axis, what do you think about that? Let me label these, and we'll show that and that distance at that and that distance. So if I label this as R1 and this as R2, so what about R1? What do you think? Is that the inner radius or the outer radius? For sure, if you said inner radius, you'd be correct, right? You're rotating this region about this axis, so that's the inner radius. And the blue curve, or the y equals x squared, is the outside radius. So let's write that down. We have R1 as the inner radius, and R2 as the outer radius. And so let's write them out. So this is the distance from this axis of rotation to the y-axis. We know it to be 3 units, right? Never mind it's negative or positive. It is 3 units. So 3, the inner radius is 3 plus the distance, that distance, right? So we need to figure out what that distance is, and I haven't done that yet. Well, for that, we have that. For the inner radius, we can, it's for the blue curve that I haven't yet figured it out yet, for the quadratic curve. So for the inner radius, we can simply say 3 plus y. Because for that line, the straight line, it's just y equals x. So depending on the axis of rotation, we will use either x or y. In this case, we will use y because we're going to say dy, right? If you take those regions, those washers, they have thickness dy or delta y, which we will then integrate from 0 to 1 to that height. Okay, so now for the outer radius, we will need to rewrite this expression in terms of x. Right now it's been written in terms of y. So let's do that. So we have if y equals x squared, then to write this expression in terms of x, we'll have to take the square root of both sides, right? So y raised to 1/2 power, which is the same as taking the square root, and x squared to 1/2 power. We end up with, let me rewrite this, so x is on the left, x is equal to y to 1/2 power, or x equals square root of y. Okay, so then using that, we can then bring this information up here and use it in that setting up of the outer radius. So that would be 3, right? The distance from the axis of rotation to the y-axis is just 3 units, plus that distance x from y-axis to the curve, and that would be square root of y. So this would be 3 plus square root of y. Okay. All right, so now we have all the information we need. So let's set up the integral for calculating the volume of such solid. All right, I'll just start here. So the volume will be we're integrating washers that go in this direction from 0, 0 all the way to 1, 1. So it'll go from 0 to 1 along this axis of rotation, which is parallel to the y-axis. Then of course pi times outer radius, which is 3 plus square root of y squared minus 3 plus y squared. And that is, of course, dy. Okay. So this is our integral. Again, if you expand these binomials squared, subtract them, combine this like terms, all of that algebra will lead to very easy terms to integrate. So simplify, integrate, and calculate the volume. So depending on the type of question you get on the exam, if it asks you to just set up the integral, this is where you would stop and you get full credit. But if it asks you to set up the integral and then calculate the volume, you would take this and calculate this definite integral all the way. Okay, so that is that. Okay, so this was application of the disk and washer method. We will do more, in addition to these examples that you saw, we will do more examples in class when we meet during the regular scheduled class sessions. Now, let's switch over to calculating the volume of a given solid. So in other words, we already have a solid and we're asked to calculate the volume of that. So that's another situation. Of a given solid. And let me add without a specified axis of rotation. In other words, we'll have to do more here. We'll have to do more thinking with problems like this, because then, given the solid, we want to come up, everything we did so far, we basically created either a disk cross-sectional area or a washer cross-sectional area, and we integrated those two types of cross-sectional areas. Now, with these types of problems, you either might have a disk cross-sectional area, a washer cross-sectional area, which you'll have to determine which one will apply, or if neither one will apply, then we'll have to use elementary geometry to establish a cross-sectional area that is neither a disk nor a washer cross-sectional area, but it's a cross-sectional area that you can then integrate over a certain interval. So let's just create a bullet list of things that we should be mindful here. So we want to identify, in situations like this, we want to identify a cross-sectional area. And that could be either in terms of x or in terms of y of the given solid that we have. And use either the disk method or the washer method, or elementary geometry write that section, cross-sectional area, in terms of the quantities that you're given in the statement of the problem. So of the given quantities. Okay. Then once we have that cross-sectional area, the hard work has been accomplished. So all we have to do then is integrate it. So take the integral of ax well, along the x-axis, so that's when we'll end up with dx, and then or the cross-sectional area as a function of the y or vertical values along some axis of rotation that is either on the y-axis itself or parallel to it, and along the y-axis, in which case we will have dy. Of course, if you have the disk or the washer method, then we'll use those formulas that we already discussed. But if you use the elementary geometry, then the cross-sectional area that you have itself, then that is what you will have to then integrate. And we will look at a few examples of it here, and then also when we meet in class. Okay, so let's see. We can go through some of these examples. This should be 8. That should be 8. All right, so we have one such example here. In these problems, so the first thing we want to do, just like before, we want to sketch the region. Even if the problem doesn't ask you, please go through this step. It's very helpful to setting the problem up correctly. Find the volume of the solid. So this will be the general title for every example that we'll do from this point forward, and I'll just label this next example as A, and then we'll do another one as B, and so on. And so this one we have the curve 1 minus x squared and y equals 0, and we want to take this and rotate, or we want to have a solid that has been generated from these curves about the x-axis. Okay, right here, you know you're going to have to use dx, right? So this one we can use this equation as it is. We don't have to write x in terms of y. Y given in terms of x is just good enough in this case. So let's draw a simple example of this situation. I'll draw it in this corner. So we have x have y, and 1 minus x squared is simply upside down quadratic equation with the vertex at the origin moved up. The vertex is moved up 1 unit, right? We remember that from transformation of functions from pre-calculus. So we have, and this is, it's saying that this and y equals 0. So that will have to stop at this x-axis, or y equals 0. So I will just try to draw this to scale as much as I can. And then another one like that on this side. Something like that. So that is that curve. And y equals 0 is this line, the x-axis, of course. And we have, if I shade this region lightly with my pencil, that's the region that is being rotated about the x-axis. So this is an example, again, of a disk method, but we will do a mix of these problems. We will do one example of a disk method, maybe a couple more, maybe one as a washer method, and then another one as a mix of something that we'll have to use, I guess. Let's see, what do I have here? Another example I have, and we will do one where we have to use a little bit of elementary geometry, just using a slope and an equation of a line, things like that. Really simple one. And we'll expand on that in the examples we'll do in class. So here, when we rotate about the x-axis, then we have to establish what these points are, where these points are, so we know the limits of integration. Okay, so basically let's establish the x-intercepts. That's what we want to find out. So we already know that the y-intercept is easy to find. If you just substitute for x with 0, you get y equals 1. So we already know that is 0, 1. And then to find the x-intercepts, so the solution, I guess, starts with the picture. So that was the, let me draw some line here, maybe with my pencil, lightly. So that was what was given to us, and everything below that line is what we're doing to solve the problem. Okay, so, and then intercepts would be, so 0 equals, in that equation, 1 minus x squared. So from that we have x squared equals 1, and then x equals plus or minus 1. So we have 1, 0 and negative 1, 0 as our x-intercepts. So let us identify that. So this would be minus 1, 0, and that would be 1, 0 right there. Okay, so now we know the limits of integration. Negative 1 to 1, right? And when you rotate this region about the x-axis, of course, you're going to use the a disk. So the cross-sectional, so use the disk method. I know I'll do a horrible job if I draw this, but you can visualize this, that if you're rotating this region about the x-axis, you're just going to get a disk, right? There's no hole in the middle, so that simplifies things quite a bit. All right, so we will set that up using the disk method. We have the volume going from -1 to 1, and pi times the function that generates that would be this 1 minus x squared, and we're doing this along the x-axis, so dx. Okay, so the rectangles that are being involved in this integral, if you're trying to visualize what this integral is doing, they're going to be vertical rectangles, or vertical discs, not rectangles, sorry. So let me do one. I'll just do one right here. So it will be something like that. See, I knew I'd be terrible at this, so like that, and then it would have the thickness of this disk would be delta x. So if I give it a little bit of depth here, maybe here, right, like that, so that thickness right there is delta x, which would translate into dx, and then we have disks going through from -1 to 1 to give us the volume that we're calculating. Okay, so this is a single disk. That is a single disk. Okay, so let's carry this integral all the way. So we'll have, I'll just start from here then. So we have the volume going from, so we have pi, let's expand that. So we have 1 minus 2x squared plus x to the 4th power, and then dx, right? And then integrating that, we will have pi times x minus 2/3 x cubed plus 1/5 x to the 5th power, and of course from -1 to 1. And then we have, so I hope you did this, you paused the video and went through all the solution on your own, and you're comparing your work with this. But this is what I got. I got 1 minus 2/3 plus 1/5 minus 1 plus 2/3 minus 1/5. And then of course this is, so we have, after simplifying all, distribute this minus into that and simplify everything, you get 16 over 15, and then this would be equal to, so volume is 16 over 15 pi. Okay, so this is where we would have that. Okay, so this was familiar, right? So we had to just use the disk method. The next one will look familiar as well. So here we want to this curve, and this curve, and this curve, the region that is enclosed by all these three curves, and rotate that region, and let me say rotate about y equals 2. Okay, so let's first find what does the region look like that is enclosed by these three curves. So I will draw my graph here. Please feel free to pause the video, sketch the curves and the region, and go through the whole thing, and then spend maybe 15-20 minutes on it, no more than that, and then compare your work with this. I'm sure our work will agree, and if it varies, it's going to be a little bit variation. Okay, so that's that. Now this curve, this exponential function, because of the negative x, it's going to be a declining or decreasing exponential function. So I'm just going to draw it like that. If it was positive, you know it would go like that, right? An increasing function. But because of that, we will have this kind of scenario, like that. And then so this is, so this is y equals e to the negative x power, and then y equals 1 would be, well, we know that that's 0, 1, right there. That's the y-intercept. If you replace x with 0, you get 1. So we know that y equals 1 should go through that point. And I will use my red ink to do that. There it is. So we have our y equals 1 line, and then x equals 2 would be somewhere here. Let me try to keep this to scale at least, because I didn't do it for the other drawing. So if that is 1 unit, then 2 units would be roughly here, somewhere there. And then I'm going to use, again, my red ink to draw x equals 2. Like that. Okay, so this would be x equals 2. So the region that we have enclosed by all these three curves is this here. Maybe I should use my highlighter in this case. I worry about smearing the ink all over the place, so that's why I use my pencil more often. That's the region we'd like to rotate. I'm sure as soon as you figure out this region, you know this is going to be a washer method, right? So we are rotating this about y equals 2. So y equals 2, let me draw that with my black ink. Y equals 2 would be somewhere here, like that. So that is y equals 2. And let me quickly, with my thick marker here, identify that as the axis of rotation, right? Okay, so now we have to establish let me right off the bat say that, and I want to divide what we were given at the beginning from what we're doing to solve this. So anything below this pencil line is part of the solution. Okay, and so So we want to use the washer method. And so let's see. We need to figure out the inner and the outer radius, or radii. So let's see. We have, I'll just do a little arrow here and then do a little arrow here. Right, like that. So let me call this R1 and R2, right? So what do you think about R1? Is that while as we rotate this region about the y equals 2 line, is R1 the outside radius or the inside radius? It's going to be the outside radius, right? So let's just say then R1, the outer radius. So what is its measure? So we know that from this y equals 2 line to the x-axis is 2 units. Now 2 units, this is going to be, the outside radius is going to be shorter than 2, right? It doesn't reach, this curve doesn't reach the x-axis. So 2 minus this curve, which is represented, this y equals e to the negative x represents that height. So 2 minus that distance will be the outside radius. So 2 minus e to the negative x power. Now R2 is clearly the inside radius. And that'll again be 2 minus the distance, the vertical distance that is represented by this y equals 1 line. So 2 minus 1. I'll just write it as that so it's clear where that is, that if I write 1, where that quantity is coming from. It's coming from that difference. All right, so now the integral then, it will go from, so we want to integrate from, let's see, about the, so this y equals 2 is parallel to the x-axis, right? So we're integrating from that point, or that point, which is 0, 0, if you, so that at that point right above this, all the way to that, which would be x equals 2, right? So that point, this is 2, 0. So we're integrating this region from 0, x equals 0, to 2, about the line y equals 2, which is parallel to the x-axis. So let us set up the integral then. So this is the limit of integration from 0 to 2. All right. So I'm going to write that all here. So we have 0 to 2 pi, let me bring this a little bit down, times the outer radius, 2 minus e to the negative x power, squared of course, minus the inside radius, or 2 minus 1 squared, and then dx. Right? If you take the washers, and I'm not going to draw them because I will mess up the drawing, but if you visualize washers going from x equals 0 to x equals 2, they will have thickness delta x, which would translate into dx here. Okay, the thickness of the washers will be delta x. Okay, so let's expand these simplified terms, and hopefully if you pause the video and did this work before me, hopefully our answers agree. So this is what I got. Putting the pi in front, 0 to 2, I expanded this combine the like terms, and this is what I got. 4 minus 4 times e to the minus 6 plus e to minus 2x power minus 1 dx. Okay. All right. So now we have one more thing to do to simplify this, right? So we have, I actually should have done that too. So I should have just done 3 minus that plus that. But it's okay. So 0 to 2 pi times 0 to 2, 3 minus 4 times e to the negative x power plus e to minus 2x power dx. Okay. All of these terms are easy to integrate. So let's do that. We have the volume equals pi times, this is simply 3x. This will be simply positive 4 times e to the negative x, right? The natural exponential function, we know how to integrate that. So plus 4e to the negative x power. And this, of course, we have to make, because by the chain rule, we're going to get a negative 2 from this. So when we integrate, we want to make sure that we get rid of the minus 2. So minus 1/2 times e to minus 2x power. And then 0 to 2. If you have any questions about these steps, I'm pretty confident you know how these things are simplified and how these integrals are calculated. But if you have any questions, just let me know. And then let's calculate that. We will get the volume equals, so here's what I got. I got 6 plus 4 e to negative 2 minus 1/2 times e to the negative 4 minus 0 plus 4 minus 1/2. Okay. After simplifying all of this, I did this. I got 6 plus 4 times e to the negative squared power minus 1/2 times e to the negative 4 minus 7/2. And then, of course, the final result after combining the 6 and minus 7/2, we will get 5/2 plus 4 times e to negative 2 power minus 1/2 e to negative 4 power, and of course pi times pi. All right, so there we have the volume of that region as the volume of the solid of the region that is generated by rotating it along about the y equals 2 line. Okay. So let us do another, this would be page 11, I guess. Yep. So in this example, we have the curve y equals x, or that straight line. We have the curve y equals square root of x, and this time we want to rotate about x equals 2, right? And let me quickly draw a line, faint line with my pencil. So everything below that is the solution, including this graph that I'm about to draw. So given this curve, everything is going to be on the positive side, right? So from 0 and anything for x values, anything greater than 0. But we got to be careful here because we're rotating about a horizontal or a vertical line. Rotating about a vertical line which is parallel to the y-axis means that we can use dy or y as the variable of integration. So this function is okay, but this function has to be written in terms of y. So x has to be written in terms of y when we do that. You'll see. That's why I encourage you guys to graph all these situations, because they simplify, they answer so many questions that you might have. We have 0, 0 here, and then so we have this curve would look like this. And then, so this is y equals square root of x. And then, of course, the y equals x would be dissecting the first quadrant, like that. And so we have this region. That. So we already know from the previous examples that kind of look like this, or partially were the same as this one. We know that is 1, 1. And we're rotating about x equals 2, so let me also draw that line. My drawing is not going to be to scale, sorry, but I will just, it's definitely not going to be to scale, but let me, I'll just do my best here, and I'll extend this x-axis. I will fix this before posting the lecture notes on in Canvas. So, but x equals 2, given these, and still not going to be to scale, but it will do the job. It's going to be x equals 2 would be somewhere here. So this is x equals 2, x equals 2 vertical line. So clearly this is going to be a washer, right? So the inner radius will be this one. I should have asked you, or I should have let you determine this. So, and the outside radius, you can see it clearly, right? As you rotate this region about this, the inner radius is going to be this, the outer radius is going to be the y equals square root of x curve. And so this is that. So this is R1, R2, and we know that, so we're going to use the washer method. And the inner radius, so let's establish that. Before that, I should actually solve this because we're integrating these washers that will result from rotating this region about the vertical line x equals 2 from vertically, right? So we're going to have to say dy along a line that is parallel to the y-axis, and it's going to go from 0 to 1. So our limit of integration is, look at the y component of these 2 points. It's going to be from 0 to 1. And it's going to be, I'm going to have to rewrite this. Yeah, let me first figure this out. So if, I'll just say if we have y equals square root of x, I need to correct this or clean this up before posting it on Canvas. So I will do that. If y equals square root of x, then we have x square this and both sides, so x equals y squared. Okay, now we are ready to write the inner and the outer radius. So r1 is the inner radius, and that is equal to, so we have from the y-axis to this vertical line, or axis of rotation, let me just do one of these symbols. So that's our axis of rotation. So that distance is 2 units from y-axis to that. Of course, that is short, r1 is shorter than that, and we know y equals x here. So it's going to be 2 minus y, and because we're taking the integration as along the vertical axis, so it'll be 2 minus y, and then let me move this up a little bit. The outer radius, it's going to be that distance again, 2 units from the y-axis to the axis of rotation. Of course, this is shorter than that, r2 is shorter than that, so 2 minus y squared, right? We just reconfigured that equation for that curve in terms of x. So 2 minus y squared. Okay, so that's that distance, and we're integrating from y component 0 to y component 1. Okay, let's do that. So we have the volume pi going from 0 to 1, and the outer radius, it's going to be 2 minus y squared squared minus the inner radius squared dy, right? So that's why these expressions were written in terms of y. All right, so expanding these and then simplifying them, this is what I have. I hope what I'm doing agrees with what you did before you watch the rest of this video. And if they don't agree, I hope you're seeing why our solutions vary. If not, please ask. So minus 4 minus 4y plus y squared, and then dy. Okay. And then I've double checked these, so hopefully there's no error here. And then, so distribute the minus, combine the like terms, and we should agree that this integral is from 0 to 1 of this integrand, y to the 4th power minus 5 y squared plus 4y dy. Okay? And then all of these are very easily integrated. So we have pi times 1/5 y to the 5th power minus 5/3 y cubed plus 2 y squared. And I'm double checking these. Yep. Okay. So then calculating, substituting for y with 1 and then 0, this is what I ended up with. I ended up with pi times 1/5 minus 5/3, of course, and then plus 2, and then the 0 everything will cancel, so that's all we have. And then after taking the common denominator, all of that, and simplifying, I have 8/15 pi. So there's that volume. I hope these are helpful in making sure that you know how this procedure works. Let's let's do one where we have to use basic elementary geometry. So let's do one like that. We'll do more in class. So, and your book has done several examples. I think at least one example, or maybe two. So here, in this example, we want to find the volume of the given solid. Okay, I'll try to draw this as best as I can. The solid that we are given looks like this, and then it's got two sides. So it's got a side that goes like this. Well, maybe I should draw this one first. So it goes something like this, and then one on this side that looks like that, something like that, and it's a circle on top, and it's going to be a circle on the bottom, like that. And then I'll try to give it a little bit of depth to make it look like a solid that it is, so that, and this is just a circle at the bottom as well as the top. And so from the center here, center of this circle, and the radius of that, the circle at the base, is given to us in capital R. So that's the radius of that. And so that is, and this one is being given to us as lowercase r. So that is that. And lowercase r. And we are told that, so that's basically the information we have. And the other thing that we know is that we know that this height, this distance, maybe I should put that center as a little bit this side, but that distance is h. That's h, is the height of that solid. Okay, so to do this, we'll have to use a little bit of very basic algebra or elementary geometry, basically. So to do that, notice that we can take a certain disk of a certain thickness to integrate from over the height of this object, right? From 0 here all the way to h here, right? But for that, we're going to need to know this distance is going to vary from r, capital R, to lowercase r. So we're going to have to know that function that generates that distance from the center of each circle to the edge of that solid. We need to know that function and then see how it will vary according to the height of this solid. So we need an equation for the side for this. So this, so figure out, I want to figure or find an equation for this line. And let's see. as a function of h, right? We're going to have to get that because this disk, it's going to have a varying radius depending on the height for this line as a function of h. Okay, that's what we want to do. So to do that, notice that that point has a component that we can write in terms of r and h, the information that we're given. These are the variables we're already given. So that one would be, that point would be r, right? If we situate the vertical axis or y-axis directly at the center of the solid, we will have, so let me actually do that. I think I should. Let me superimpose the Cartesian coordinate axes on this. So if I do that, so the origin would be that. So the axis, it's something that we're superimposing, and it's not lining up with this one side, and that's my error because my drawing is really not that great. But just put the center of the base of this object at the center of at 0, 0. That's the point I'm trying to make. 0, 0. And then if we do that, then we can say label these points with their coordinates. So that one will be r comma h, right? R comma h, it's that point. And this point will be r, capital R comma 0, right? R comma 0. So now, and remember, this objective of what we're doing is we're trying to find an equation for this line as a function of the height of this solid. So now, from this point forward, we can just calculate the slope of that line and then figure out the equation of that line. Okay, so let's do that. And I want to, so the solution starts with all these things that I've added. And then we have the slope, so this is what I have. Slope is h minus 0 divided by r minus, lowercase r minus capital R. So we end up with h over lowercase r minus capital R. So using the familiar equation we learned back in basic algebra, right? Y minus y1 equals m times x minus x1. And pick one of these points, so we can pick that one, and r comma h, and that slope that we just calculated, we can find that this line. So y minus h equals that slope times x minus, of course, r. So one thing is that let me, so this will lead to a y equals all of this plus h, right? So h over r minus lowercase r minus capital R times x minus r plus h. Now notice that because we're going to integrate that expression along the vertical axis or along the height h, we're going to have to rewrite this equation in terms of or write it as x in terms of y. So let's do that. So we want to solve this equation for x. Okay, so let's do that. And I have multiply both sides by, well, let me actually set the stage for that. So we will be integrating along the y-axis. Right, so we must have the equation given as x in terms of y. Okay, so let's solve this equation for x. All right, so we have multiply both sides by r, lowercase r minus capital R. And we have h that plus h times that. Okay, now distributing everything into the parentheses, we have yr, so capital R, right, and then so far so good, and then we have, so these two will cancel, right? This term and that term will cancel, and we end up with let's put this plus HR equals XH, or that one, right? And then X, of course, oops, let me move this up. X is YR minus Y capital R times that plus HR divided by H. Okay, so now actually, so we can, let's see, if we simplify this a little further, we will get, so we will have, let's see, so let's simplify this a little bit. We end up with capital R that Y. Okay, so like that. So having that equation, then we can then rotate that line which traces that disk, and the disk is gonna be integrated along from 0 to h, from 0 to h. So as we rotate that equation about this center from 0 to h, then it'll trace a disk all the way from 0 to h. With the equation that is tracing the edge of each disk formed, well, the equation that is tracing the edge of each disk, each incremental disk with thickness dy, it's going to be traced using the equation we just found for this line, x in terms of y, okay, or that. Okay, so then, and we know, let me actually mention that, so the cross-sectional area will be a disk. All right, so that will be from 0 to h, and we will integrate this expression, and pi, of course, right? So pi times Okay, so let me move to the next page. I'm running out of space here. That. So we have this pi in front, integral from 0 to h, and then we're integrating with respect to the y, so we end up with, well, let's expand this first. So we have this squared here. So we have r squared minus 2r times all of that, r minus r divided by h times y plus all of that squared. So we have this quantity squared y squared. And then of course this is dy. Okay, so integrating this expression with respect to y, we have pi times, that's simply let's see, so r2, that would be r squared y minus 1/2, right? And that 2 will cancel with that 2, so it'll be minus r, let me write it down, minus r, and this would be y squared, divided by 1/2, which would cancel with this 2, so we end up with minus r times r, capital R minus r, divided by h, y squared, plus, of course, y cubed divided by 3, right? Or 1/3 times y cubed times all of that. So we have 1/3 times all of that y cubed. And this, of course, is being integrated from 0 to h. Okay, so then let's calculate this quantity with, well, let's actually, can we factor out some things? Yeah, we can. So let's do this. So we have, well, after we evaluate this, well, this is what we're going to get. Let's just evaluate this function. And then so we get, so this is what I have, r squared h minus, minus if we have, well, if we substitute for y squared, this would be h squared divided by h, we'll end up with h, right? So minus rh times capital R minus lowercase r, plus, again, this would, things would simplify here, this would be h cubed times h squared, so we end up again with h. So 1/3 h times this quantity, okay, after simplification. And 0, of course, then it will make all those 0. So we're good there. We don't have any more terms after that. So can we kind of factor, it looks like we can factor a bunch of things, right? H, and let's see, so pi, which is out here. So even 1/3, we can pull this out, and so, but we'll have to have a coefficient 3 for each of these, right? So let's pull all of those out, and I will do that. So let's factor, so we have 1/3 and h of course, and then pi h times all of those quantities. So we have 3r squared, all right, 3r squared minus, again, 3r times capital R minus lowercase r, plus, then we have just r, capital R minus lowercase r squared. Okay, and that like that. So then, all right, so if we distribute this, let's do that and then simplify things a little more. So we'll end up with, so we have 3r squared minus 3r squared plus that, plus r squared minus plus r squared, right? Like that. Just double checking here. And yeah. And then so we end up with volume equals 1/3 pi h times, so these two add up to 0. These two will give us just capital R, and then r squared, this r squared, and that r squared. So we have r squared, capital R squared, plus that term, plus r squared, and that's that. Okay, so there's the volume of that solid. If you take a look at these types of problems where we have to figure out a cross-sectional area, each one of these problems is unique. But some of them you can use similar triangles even to find the equation for the cross-sectional area, especially if you have a pyramid. If you're calculating the volume of a solid that is a pyramid, then or a portion of the pyramid, then that would be one of the possible approaches we can use. So I hope this has been helpful, and thank you for watching this video until the end. For now, have a nice day, and I'll see you again